Let's continue to think about some examples of using the chain rule together with our other rules that we've had before. So we're just going to kind of look at a few different types of problems here, and I'll show you examples of how I think through them, and then you'll gain more practice with working with these rules yourselves, of course, on the homeworks and things like that. So let's suppose that I want to do the derivative of, let's say, e to the x times the sine of x. Well, this is not one that involves the chain rule. I'm not saying all the examples of today are going to involve the chain rule. The point is we want to just look at all sorts of different examples here. This is one where I see I have a product, so I'm going to use the product rule. So the derivative of e to the x is still just e to the x. And then I'm going to have e to the x times the derivative of sine x, which is cosine x. So this is going to become e to the x times sine x plus cosine x. And there we go. We've been able to do this one by using the product rule. Here's another sort of example of finding a derivative. Maybe we have to do something like the derivative of x times e to the tangent of x. So in this case, well, this is going to be the derivative of x, which is 1, times e to the tangent x. And then we're going to have plus x times, now the derivative of e to the tangent x is going to be the derivative of tangent, that's actually secant squared x, times e to the tangent x. And we can factor in e to the tangent x out of this, and this becomes 1 plus x secant squared x. So in this case, we had to apply the product rule, but we also had to apply the chain rule here. Now, in other situations, maybe we have to apply some other types of things. Let's suppose that I have, say, the derivative of x squared plus 3 divided by e to the 5x. Now, there's actually a couple of different ways of doing this problem, and I want to show you both of them because it's good to see how sometimes, like, there's always a specific way that you can go. There's always some rule that you're going to be able to use, but sometimes there's more than one rule, and you can kind of think of this in two different ways. So I can do this by using the quotient rule, and then I would have f prime times the denominator, that's 2x times e to the 5x, minus f, the numerator, x squared plus 3, times the derivative of the denominator, that's 5e to the 5x. And then on the bottom, when I square this, I get, well, e to the 5x squared. We'll leave it like that for now. This is going to become 2x minus 5 times x squared plus 3, e to the 5x over e to the 5x squared. We can cancel out one of the e to the 5x's, and we are left with negative 5x squared plus 2x minus 15 divided by e to the 5x. But there's a second way that I could think about this instead of there's a second way that I can think about this instead of using the quotient rule. I could, if I wanted to, have rewritten this in the following way. I could have said, before I go into this problem, let me rewrite this as the derivative of x squared plus 3 times e to the minus 5x. And now I can just use the product rule, because this is now going to become 2x e to the minus 5x, and then we're going to have minus x squared plus 3 times 5 e to the minus 5x. Now, if you rewrite this a bit, you'll see it's actually equal to what we got using the quotient rule. It's not really that difficult to do. Just simplify this out a bit. But it looks a little different this way. So it's important to remember that you can end up with the same answers, just written in slightly different formats, and that's fine. Now, this also applies in some other types of situations, like let's say that we had the same kind of thing, but we're dealing with the reciprocal. So maybe I'm dealing with the derivative of e to the 5x divided by x squared plus 3. Well, I can do this using the quotient rule, and I would get 5e to the 5x times x squared plus 3 minus e to the 5x times 2x divided by x squared plus 3 squared. And then I could simplify this, and I would get my answer from the quotient rule. But the interesting thing is, now remember at the end of last time I showed you how the quotient rule is really a consequence of the product rule and the generalized power rule, which is really a special case of the chain rule. So I could alternately solve this problem by doing the following. I could say, let's turn this into the derivative of e to the 5x times x squared plus 3 to the minus 1. Then this is going to become 5e to the 5x times x squared plus 3 to the minus 1 minus e to the 5x times x squared plus 3 to the minus 2 times 2x. And then, of course, we can simplify this out a bit. Now, it's not necessarily immediately obvious that these are equal, but combine them, write them with a common denominator, and you will get the same thing as we got using the quotient rule. So, once again, there's different ways of thinking about it. Some people like to use the quotient rule. Some people like to just use the product rule together with the generalized power rule. I don't really care which way you do it. It's good to know how to do it both ways, but whatever works for you is fine with me. So let's look at some other examples here of types of problems that we can ask at this point. Let's say that we want to find the tangent to y is equal to, let's say, e to the x squared minus x when x is equal to 1. Okay, well, first of all, we need to know the point that it's going through. The point is going to be 1 comma e to the 1 squared minus 1, which is 1 comma e to the 0, or 1 comma 1. So that's the point that we're going through in this problem. The next thing that we can then ask is, well, what is the slope? So to find the slope, we can take the derivative here, and this is going to be 2x minus 1 times e to the x squared minus x. And if I plug in x equals 1, y prime evaluated at 1 is going to be 2 times 1 minus 1 times e to the 1 squared minus 1. And this actually just comes out to be a slope of 1, interestingly enough. So my equation is going to be y minus 1 is equal to 1 times x minus 1, which actually simplifies, in this case, to y equals x. So there's my tangent line to this particular equation. And of course, you can do this kind of thing, more generally, right? I happen to pick this example, but we can do this with any particular functions that we care to do. Another example that maybe we could do is, let's say that we want to find the tangent to y equals sine of x squared when x is equal to square root of pi divided by 2. Well, we need to find the point first of all. The point is going to have an x-coordinate of radical pi over 2, and then a y-coordinate sine of radical pi over 2 squared. So this is going to be the square root of pi over 2 sine pi over 4. Now, does everybody remember sine of pi over 4? Do you remember your unit circle stuff? If you don't, you may want to go back and look that stuff up again, because it is going to be important for us to remember those things about trig functions. And sine of pi over 4 is actually just going to be square root 2 over 2. So this is going to become, excuse me, square root pi over 2, square root 2 over 2. So there is my point. Now what about the slope? Well, y prime is going to be equal to 2x, which is the derivative of x squared, times cosine x squared. And I get that by just using the chain rule. So y prime evaluated at square root pi over 2, this is going to be, why am I suddenly confusing myself? 2 times the square root of pi over 2 cosine pi over 4, which is going to be square root of pi times the square root of 2 over 2, or square root of 2 pi divided by 2. So that is going to be my slope. And now that I have my slope and my point, I can write my equation. So y minus square root 2 over 2 is equal to square root 2 pi divided by 2 times x minus the square root of pi divided by 2. Now, this might seem like a bit of a confusing problem because we've got all of these square roots of pi floating around. We've got these square roots of 2 and things. The last example didn't have that, but I want you to notice this example, it's really not that much different than the previous one. Yes, the numbers are a little harder, but the essence of what I did was exactly the same in both cases. The procedure is the same. It's just that, yeah, we end up with some square roots floating around and things like that, but that's not really such a big deal as you might think, okay? As long as you do all of the process correctly, that's fine. Now, by the way, you might be wondering, like, should we leave the answer? Like, do you put this into a decimal approximation? I don't like using decimal approximations. Because the thing is, we can always get a decimal approximation at the end if we want to. But you can't go back from a decimal approximation to an exact answer. So I prefer to leave everything exact. And normally, when I'm teaching this and have people hand in work in person, I have them give me the answers in exact form, unless I specifically say to give me a decimal approximation. But of course, in some applications, a decimal approximation is fine. It's just, again, it's good to know how to give the exact answer because then you can always make the decimal approximation if you need to, but you can't do the other direction. Let's take a look at some other types of derivatives and just kind of what I'm going to encourage you to do is take a minute on each of these examples before you watch what I do and see if you can figure it out for yourselves. So how would we go about taking the derivative of, let's say, the tangent of e to the x? Take a moment to see if you can figure this out. Well, the answer is going to be you use the chain rule. The derivative of e to the x is just e to the x. The derivative of tangent is secant squared, and that gets evaluated on e to the x. So there we go. We've got our derivative written down by using the chain rule. Now, what if we took that same example, but we made things just a touch more complicated by saying, I want to take the derivative of the tangent of x times e to the x. So see if you can figure this one out. This one takes a little bit of extra work because this is going to be the derivative of x times e to the x times secant squared x e to the x. And this derivative of the x e to the x, now all I've done so far is to apply the chain rule. But to find this derivative, I need to use the product rule. So this is going to become e to the x plus x e to the x, secant squared x e to the x. If you wanted to, you could factor out an e to the x, and you have e to the x times 1 plus x, secant squared x e to the x. Now, this was a little more involved because we had to use multiple rules together like this, and that's not uncommon. You have to end up using a bunch of different rules to get through your problem in quite a few different situations, I'd say. But it's not really that big a deal, okay? It's really just a matter of breaking it down piece by piece. So we broke this down using the chain rule, and then we broke down the new derivative that we needed to find using the product rule. The same kind of thing we've seen before where we did things like, we have a derivative, we can use, say, the quotient rule, but then to do one of those derivatives, we need to use the chain rule again. So yeah, it's the same kind of thing. Just figure out what rule to use next. Let's take a look at another example here. Suppose that I want to find, and again, I want you to take a minute to try this for yourselves before you watch how I do it. So see if you can find the second derivative of sine of, let's say, 3x to the fourth. This one might take you a minute. All right, so let's first of all find the first derivative of this thing. Now, the first derivative is not too difficult because this just relies upon using the chain rule. And it gives me 12x cubed cosine 3x to the fourth. But now I need to do the derivative of 12x cubed cosine 3x to the fourth. And this is just a little bit more complicated because now I need to use the product rule and I need to use the chain rule. So I can rewrite this as, from the product rule, I'm going to get 36x squared cosine 3x to the fourth. And then I'm going to get plus 12x cubed times the derivative of cosine 3x to the fourth. So I've applied the product rule here, and I did have to write things on 2 lines. I'm sorry about that, but as you can see, no space. Well, now I just need to do this derivative by using the chain rule again. So we're going to have 36x squared cosine 3x to the fourth, and then we're going to have minus 144, because we're going to multiply by another 12x cubed here, and we get a negative because the derivative of cosine is negative sine, and then we have 3x to the fourth inside of it. So, I've lost an x to the sixth. We can actually factor out here 12x cubed times 3 cosine 3x to the fourth minus 12x cubed sine 3x to the fourth. Okay, so as you can see, this was a much more involved example. But, and here's where I want to kind of give you some words of encouragement. What you're doing when you do these examples, they get long. The key is to just not panic. I think one of the problems that some students have is you start doing something like this, it looks like it's turning into a lengthy mess and it feels overwhelming. The key is to remember that it's really just a lot of little pieces put together, and every one of those pieces is something we know how to handle. Taking the first derivative here, that's just the chain rule, so that's fine. But now we have to take the derivative of this thing, and that starts turning into a mess because I had to use the product rule. Well, then after using the product rule, I also have to use the chain rule. So again, it seems like it's snowballing into a mess, but every single one of those things that I'm doing, it's not something that is unheard of for us to do. It's something we know how to do. And so as long as I keep track of that, and I don't let myself get overwhelmed by the fact that this is turning into something rather lengthy, I will get through to the end and get my answer. And maybe the answer won't be the neatest or most compact thing. Our answer here is pretty complicated. But, just try not to let yourself panic about those kinds of things. You might also wonder, how essential is it? Oh, one thing that it is essential that I do is not write x squared where it's supposed to be an x cubed. Probably you've all been looking at that thinking, why on earth is that a square instead of a cube? Oh, no, that is supposed to be a square. Never mind. That is supposed to be a square. This is supposed to be squared, and this is supposed to be x to the fourth. There we go. I knew that I had made some sort of a mistake there with this sort of thing. Yeah, that was supposed to be squared because it came from differentiating this. But then when I did the factoring, I would have needed to pull out just an x squared, and I pulled out an x cubed for some reason because I'm an idiot or something. So yeah. Actually, this gives you an illustration of where most mistakes are going to end up happening for you in these kinds of problems. They come because, I was so focused on the complicated side of things, so to speak, that I ignored basic adding and subtracting of really small numbers. And that is honestly where I would say 80 to 90% of the mistakes that I make and that most other mathematicians come from. We do the hard parts correctly, and then we get confused over something that seems trivial because we don't pay enough attention to it. So this serves as a good warning to you. Pay attention to the seemingly easy parts as well. And other than that, just keep track of everything that you're doing and you'll be okay. Now, let's take a quick look at another sort of special case. Actually, we already took a look at that, didn't we? I'm trying to think if there's another special case that we want to look at of the chain rule or anything. No, I think that we're all set with that. So, yeah, I think what I'm going to do here is I'm going to say, rather than just sitting here and watching me run through a few more examples, I think the best thing to do is for you to look at some examples, like go onto the Paul's Math Notes website, and look at their practice problems for these types of derivatives and try them out yourselves. And then if you have questions for me, you can ask me. But I think it's better for you to sort of get the experience of trying to work through them. And then if you get stuck, we can provide you help. If his notes don't help you enough, I can answer your questions rather than just kind of doing more random examples here, okay? So we've gone through several examples that kind of illustrate all the different, well, not all, there's all kinds of combinations, but many of the different combinations. Actually, I do know one more example that I'd like to do for you, actually. Let's do this one. Let's suppose that I want to find the derivative, because we haven't done anything quite like this so far, I don't think. Let's suppose that I want to find the derivative of cosine of, let's say, x squared divided by x plus 1. Well, I use the chain rule. This is going to become the derivative of x squared over x plus 1 times, now we're going to pick up negative sine x squared over x plus 1. We get the negative from taking the derivative of cosine. To do this derivative, we need to use the quotient rule. So this is going to become 2x times x plus 1 minus x squared times 1 divided by x plus 1 squared. And we pick up a negative sign from this, and it's multiplied by the sine of x squared over x plus 1. So in this case, we had to do the chain rule first, and then within the chain rule, we then got a derivative that involves the quotient rule. So this is kind of another example of how the rules can be used in any combination. And it just depends upon what the problem is, which combinations you're going to need to use. Of course, once again, I could have done this not using the quotient rule. I could have done this by using the product rule and the generalized power rule. Also, we should probably finish this out and simplify it, because this becomes 2x squared plus x, but 2x squared minus x squared leaves me with just x squared plus 2x, and then on the bottom I have x plus 1 squared. Oh, and this is all negative, and then we have sine x squared over x plus 1. So we can kind of get our answer down to be a bit more compact there. But yeah, so this just shows us another example of using the rules in a different order, but you really just work your way from sort of the outside in. You ask, okay, how do I break down this big thing into smaller pieces? Each of those smaller pieces, how do I break those down into smaller pieces? And eventually you get to one where you say, oh, I know that derivative because that's just one of our basic derivative formulas. And then everything is in place. It's written out in terms of those basic derivative formulas, and you just simplify the result algebraically. Now, it turns out that there are a few more techniques of taking derivatives that we're going to look at, and we'll start in on that next week. And then after we go through a few more techniques and types of problems you can handle using differentiation, we're eventually going to be moving in a brief time, into why do derivatives matter so much and what sorts of things can they tell us about the functions that they're related to. But for the meantime, let me know if you have any questions, and good luck with your work.